好，我们马上开始下一个讲座。下一个讲座呢，我们是请我们的另外一位非常资深的这个工程师 Patrick Brady， 他讲座的题目是 Android 的深入剖析。下面呢，我来介绍一下这个 Patrick。依然是用英文。Patrick is a technology program manager in Google's partner solutions group, working with Open Handset Alliance members to develop Android-based mobile devices. Prior to joining Android team, he worked with Google's partners to distribute mobile application on other platforms. 刚刚那个 Patrick 告诉我，这是他第一次使用这种，就说这 computer 这个 software， 所以可能会有一些问题。我们大家看一下一会儿会发生什么。好，现在让我们用热烈的掌声欢迎 Patrick 给我们演讲。
Okay. Can everyone hear me okay? All right. Welcome to Google Developer Days, and welcome to Android Anatomy and Physiology. As Bob said, I'm a technology program manager in our partner solutions organization, and I'm working with Open Handset Alliance members today, the OEMs, to port Android onto their platforms. As part of this talk, we'll be going through some of the information Jason went over in the last discussion at a bit more detailed level. And we'll cover some of the lower level Linux concepts that apply more to the porting side than to building applications on Android. So it's a 101 level talk, but it does assume the working knowledge of Android and the Linux platform. But if you attended the last discussion, then you'll be all set. Okay, so we'll start out going through Android Anatomy, talking about the Linux kernel, the native libraries, the Android runtime, and the application framework. And then we'll go into Android physiology, or how the different pieces in Android work together. And we'll walk through how the system looks at startup, and talk about the layer interaction, how the application framework talks down to the native libraries and down to the Linux kernel. So any discussion of the Android anatomy needs to start with our block diagram, and this is what Jason went over in the last talk, and we'll go over it briefly here. But it starts with the Linux kernel on the bottom. We have the native libraries, the Android runtime and Dalvik virtual machine, the application framework, and the applications. So let's go through each of these in a bit more detail. First, we start with the Linux kernel. So the first thing to really clarify, and this is something Jason mentioned in the last talk, is that Android is built on the Linux kernel, but Android is not Linux. Okay, so we have no native windowing system, right? All applications written for Android need to be written using the Android application framework to display Windows on the UI. We have no glibc or GNU libc support. And we don't include the full set of standard Linux utilities and shell environments that you would have on a standard Linux distribution. So if it's not Linux, well, what is it? Well, it's based on the Linux 2.6.24 kernel. We started out on 2.6.23, but we've migrated to 24, and we will be holding at 24 for the first commercial launch of the product. We have a patch of kernel enhancements, or added drivers that we've added to the kernel. So why the Linux kernel? If we're not using Linux and the whole windowing system, and Linux as an operating system, what are we using it for? Well, like Jason said, it gives us great memory and process management. It gives us a great permissions-based security model that's seen 15 plus years in hostile environments, right? So we know that the Linux security model is robust and can withstand a lot of the malintent attacks. It has a proven driver model, and so this gives us a way to plug in new peripherals onto the device. And typically, with Linux expanding in the mobile industry today, you have drivers already written for a lot of these peripherals, and so you can plug them into Android very easily. It has support for shared libraries, so that different developers can build different components and add them into the platform at a very low level. And on top of all this, it's already open source. And so we have a thriving community of Linux kernel and driver developers who are already contributing to that platform. So it's a great base to start from. And since we want to open source the entire Android platform, this was really a great choice for us. So talking through some of the kernel enhancements that we have. We have an alarm driver that basically allows you to set an alarm on a monotonic time base that will allow the system to wake up and perform some operations. We have our anonymous shared memory driver, AshMem, which allows us to manage cache and temporary files at the kernel level instead of for each application. We have the binder driver, which we'll get into in a second, power management, a low memory killer, the kernel debugger, and the logger. We'll talk about two of these in more detail, the binder driver and power management. And these are the ones that really have faced a lot of questions from the Linux community, and so I'd like to dive down into those in a bit more detail. So the first one, binder. Well, the problem that we have on Android, or not the problem, but the architectural decision that we've made, is that applications and services each run in separate processes. And this is very important because it's part of our security model, that no single application or service can take down another application. They run in separate processes and they run under separate user IDs. But they need to communicate between each other. Applications and services need to be able to share data and call each other to produce an end-to-end function. But IPC, or inter-process communication, can introduce a lot of overhead and security holes. And so we needed something that would solve these problems on Android. And what we've chosen is Binder. It's an IPC, or inter-process communication driver. It's based on the Open Binder platform that we've taken in-house. And it's a driver to facilitate inter-process communication. It uses shared memory to pass data structures back and forth between processes so that they copy once to shared memory and don't need to be copied into each individual process which they are being shared between. It uses a per-process thread pool that the binder driver manages so that each process doesn't need to worry about responding to different, keeping threads alive to respond to different processes' requests. Those are all managed by the driver and handled seamlessly. It supports reference counting and mapping of object references so that you can do things like recursion between different processes. And if you pass an object back from process A to process B, and then back from process B to process A, it won't actually copy that memory over twice. It will just pass the same reference back. And it supports cleaning up these objects once they are no longer used by either process. And it also supports synchronous calls between processes. And that's important because it allows you to keep the same programming model that you use in a single process environment and use that across processes. You call a function, you wait for it to return, and then you continue processing. The good news is, as an application developer, you don't need to worry about the low-level details of Binder. So if you build your services using the Android interface definition language, and there's a link to where you can read more about that online, that will take advantage of all that Binder provides at a low level. The shared memory high performance, the mapping of object references, the thread pool to listen to different processes' requests. All of that's handled for you. Moving on, we have the power management driver. And the problem that you have on mobile devices is that, number one, they run on battery power. Until we have solar-powered devices or nuclear-powered devices out there, and I don't see that coming anytime soon, we're going to be running on battery power. And batteries have limited capacity. I'm sure many of you here brought your battery chargers because your batteries have less capacity than you would like. And so we needed to do something on Android that would help us solve this problem at the platform level. And so what we've done is we've we've taken an Android power, or a more aggressive policy to power management. It's built on top of Linux power management. It's not a replacement for Linux power management. So all of the great infrastructure for power management in the Linux kernel, we take advantage of, and we build on top of that. It's a more aggressive model because it basically is built on the concept that if no application or service specifically requests for the processor to stay alive, then our power management will shut it down. And that doesn't mean that you can't receive phone calls, but it means that the application processor that's eating a lot of power and is doing the heavy lifting will go into a low power mode as soon as no application or service requires it. And we do the same thing for the LCD as well, or the display. As soon as no application needs it, we will shut it down to a low power mode. And so we do this through the concept of wake locks. And wake locks are, think of them as semaphores where you set a lock and that will keep power management from shutting down the device or the display. And so you can set wake locks that will say, keep the display alive because I'm showing a movie. So even though the user isn't interacting with the device, keep the display alive. Or you can set a wake lock that says, don't shut down the CPU because I'm playing an MP3 music file, but you can go ahead and shut down the LCD. And so you can set different kinds of wake locks. At the application level, you can set these wake locks through the power manager. But be careful when you're setting wake locks. You want your applications to use the CPU wisely and use power wisely. And so you don't want to set a wake lock and never release it because that's going to mean your application will drain users' batteries very quickly. And a safer way to do this as well is to do user activity, the user activity method on Power Manager. And that will let the platform know that there was a user activity at this time, and it will reset the timeout before it shuts down the display. Because of time, we won't go over all the rest of the kernel enhancements in detail for the Android platform, but we do have, we've made a commitment to open sourcing the entire Android platform, and as part of that, we've already made the Android kernel enhancements for the Linux kernel open source today. And so those you can get at git.android.com. It uses the Git source repository, and that's the same source configuration management tool that the Linux kernel uses to manage the source code. And we're already passing many of these enhancements upstream to the main Linux kernel as well. Okay, so we've covered the Linux kernel, why we're using Linux, and some of the additions that we've made to the platform. And next we'll talk about the native libraries. So the native libraries are written in C or C++, and they really provide the underpinning functionality of the Android platform, the low-level heavy lifting. I'm going to break these down into 4 main groups here. We have Bionic libc, that's our customized libc that Jason spoke briefly about. Our function libraries, and this is really just a name I'm giving them, but these are libraries that provide specific features for the platform. Then our native servers, and these are things that are running always in the background to respond to requests, and the hardware abstraction libraries. So we'll go through each of these in a bit more detail, starting with Bionic C. So what is Bionic? Well, Bionic libc is a custom libc implementation that's optimized for embedded use. And why did we do a custom version? There's glibc out there today that we could have used. We decided to go with a custom implementation for 3 main reasons. Number 1, licensing, open source licensing. It was very important to us to keep an open licensing model that was free from GPL in user space. So the GPL, the General Public Use License, is a software license that mandates that anything that uses GPL code must also release their code under GPL. It's called copyleft. And that's very bad. Well, people in the open source community will argue that, but it's bad for some people who want to build user space libraries that contain proprietary intellectual property. And so early on, working with our working with our partners, we realized that they had some things in user space that they wanted to keep proprietary. And so we wanted to keep GPL out of user space. The second issue is size. Because libc, because we run each application in a separate process, libc is going to be loaded many times. And we need to keep it very small. And also fast. Again, mobile processors aren't the same processors you have on your desktop computers or on your servers running Linux. These are small, low-power processors, and so we need these libc to be very fast. So Bionic libc, it's based on the BSD, or Berkeley Software Distribution License. It's based on a collection of OpenBSD and NetBSD and FreeBSD source code. It has its small size. It's about 200 kilobytes, which is less than half the size of glibc, or the standard libc library. And it has very fast code paths. It has a very fast and small custom pthread implementation, which uses 4-byte mutexes for locks instead of 12. And so it allows us to do things in much faster manner and much smaller, consuming much less RAM and ROM than we would if we were using the glibc. It also has some built-in support for Android-specific services, like getting system properties. So you can native libraries can just call these and get that very easily. And logging capabilities to log log a message here with priority info, or log D to log with debug. It does not support certain POSIX features. We don't support C++ exceptions because those are very expensive in terms of memory and processing power. And so we did not want to support that on these mobile embedded systems. Again, this is optimized for embedded use. And it's not compatible with GNU libc. So we have some GNU libc or glibc extensions, but not all of them in the platform. So that means that all native code must be compiled against Bionic headers. Okay, so moving on to our function libraries. And again, this is not a formal name for them. This is just something I'm using to group them together here. We'll start with WebKit. Again, we picked this because we, first of all, believe it's a great browser engine. It's the same browser engine that's powering Safari on the desktop and powering iPhone on mobile browsers today. It's already open source, and so again, that made it a perfect fit for our platform. It can display pages in full desktop manner. It can do full CSS, JavaScript, DOM, AJAX capabilities. And we really wanted a full browser on the mobile phone. Many of the mobile browsers out there just don't come close enough for what we wanted. And we've made some changes to it to support single column mode so that you can more easily read web pages on smaller displays, and to do adaptive view rendering so that it can display the text correctly for your display. The next one that I'll cover is the media framework. And this is based on Packet Video's OpenCore platform. And this contains all of the codecs that you would want to provide a rich media environment. So this contains your MPEG-4, your H.263, H.264, MP3, AAC, JPEG. All of these codecs are built into the platform in the media framework. And this will be open sourced under the Apache 2.0 license. And it supports hardware and software codec plugins. So if you have a microprocessor on your mobile device that has MP3 decoding built in, it's much more efficient to do that in hardware, both from the power perspective and the performance perspective, than to do it in software. And so we support plugging in those codecs so that applications don't need to know the difference, but they can plug in from the bottom layers and take advantage of any hardware. And the next one I'll cover again, SQLite. Jason mentioned this earlier, but it's a great solution for lightweight transactional data storage. This is also already open sourced under the public domain license. And so that's great for us because it means that, again, this is another piece we can get for free and package into the platform and make it available for everyone to use. And this is the back-end data store for most of the platform data storage that's on device. So this is what we use to store your contacts and your SMSs and your emails and things like that on the device. It's accessed through content providers, which Jason went over in the last session. So you don't need to know the details of it at the application developer perspective, but that's what's powering your data storage. Okay, so that's, again, just some of the functional libraries in the platform that are really, powering certain features in the platform underneath the application framework. Then we'll move on to the native servers. So native servers are processes that are always running in the background and provide some core system services to the platform and manage some of the key hardware components. So the first one we'll go over is Surface Flinger, or on the architecture diagram we call it Surface Manager. But this is the surface-wide, or the system-wide Surface Composer. So it handles different windows drawn by different applications running in different processes and composes them all together onto a single frame buffer device, or out onto your single display on your mobile device. So it manages really all access to the frame buffer device. It can combine 2D and 3D surfaces on a single, from multiple applications out onto a single frame buffer. It can plug in hardware acceleration for both 2D and 3D through OpenGL, yes. And it makes sure that you never write a partially displayed buffer out to the screen. So we do double buffering all inside Surface Flinger here. The next one is Audio Flinger. Audio Flinger is for audio what Surface Flinger is for graphics. So Audio Flinger takes different sounds and different audio from different applications, whether it's tone audio, media player audio, or maybe some game audio, or repeated race car sound or something like that, and controls all that access out to the single audio device on your, or not the single audio device. It routes it to either an earpiece on the handset, the speaker on the handset, or out to a Bluetooth wireless headset. Okay, so we've talked about Bionic C, which is really the driver for all of the native code, the functional libraries, the servers, and then we'll talk about hardware abstraction libraries. So I'm going to break from convention and show you a slightly different architecture diagram here to show you where the hardware abstraction layer is. You'll notice that we have it sitting above the Linux kernel here in the library space. It's written in green, so it's native C and C++ code here. And it's a user space C and C++ library, and it defines the interface that Android requires the hardware drivers to implement. It separates the platform logic like Audio Flinger and Surface Flinger from the actual hardware driver implementations. And many people will ask, especially people familiar with the Linux kernel, well, why do we need a user space hardware abstraction library? Isn't the Linux kernel your hardware abstraction layer? And all the Linux drivers your real abstraction to those peripherals? Well, the reason we decided to go with a user space hardware abstraction library was not all components have a standardized kernel driver interface. So you have things like a vibrator driver, an LED, or something like that that's on a mobile phone that you may not have a standard driver interface for in the Linux kernel. And the other problem is Linux kernels are, again, GPL, or kernel drivers are GPL, meaning that they must open source their code. And you have a lot of people on the silicon providers who don't want to open source some of their maybe audio code that is proprietary and has some intellectual property in it. And lastly, Android has specific requirements for hardware that are maybe more narrowly defined than what a kernel driver for audio, say an ALSA, the Advanced Linux Sound Architecture, would define. Android has very specific needs. And so we decided to define those in the hardware abstraction layer interfaces so that driver developers would know exactly what they need to define. Okay, so moving on to the Android runtime. Again, this sits on top of the native libraries, and it's composed of the Dalvik virtual machine and the core libraries. Remember, just like Android is not Linux, well, Dalvik is not a Java virtual machine. So Dalvik runs, it's a custom clean room implementation of a VM. And it provides application portability so that apps can be written against our SDK and will be able to run in this virtual environment on different CPUs. It provides, or it runs optimized format, DEX or Dalvik executables, and Dalvik bytecode. This is different from Java bytecode. And Java class and jar files are converted to DEX at build time. So again, this VM is not running Java bytecode. And Dan will get into a lot more detail on Dalvik later. Let's see. So it's designed for embedded environment, supports multiple virtual machine processes per device, and we'll get into that a little later and see why that's important. It's highly CPU optimized, and it uses memory and very efficiently. So like libc, we needed something that was lightweight, fast, and compact, and could run on this device, or on many devices. Sitting on top of the Dalvik virtual machine are the core libraries. So like Jason said, this gives Java developers their expected environment. It gives you all of your file, I/O, your data structures, utilities, network access, graphics, and the APIs that are familiar with Java developers out there today. We wanted to make these available, running on top of this highly efficient runtime, give developers a familiar environment to work with. Okay, moving on to the application framework. We won't cover this in as much detail because I think Jason went over this a little bit more extensively. So I'll break this down into core platform services. So these are services that are essential to the Android platform. Okay, and these are these services and framework components that, behind the scenes, this is what makes your applications work. You typically don't access them directly. They're kind of running in the background without your knowledge. So starting with the activity manager. The activity manager is what manages all of the different activities and their life cycles. So it knows when to start activities up, and it knows when to persist them to memory if the runtime resources are running low. You have the package manager, and the package manager is used by the activity manager to go through and give it information about all of the installed packages or APK files on the device. It can tell you, what intents are in a given APK file, or what classes are in there, what the application name is, and things like that. The window manager, it basically sits on top of Surface Flinger and manages the different windows and what order they should display on the device. So anytime that you start up an activity and draw things on it, that's going out through the window manager and down to Surface Flinger. The resource manager handles things like graphical assets or non-code resources that are packaged with an APK file. Content providers provide an abstraction to data access and their services that allow you to share data between different applications and services. So we have a contacts content provider, and it allows you to expose your contact information to different applications so that not everyone needs to maintain their own database of contacts. And the view system. This contains all of the standard views and widgets that you would use to build an actual application. So your text view and your buttons, and also your layouts, so that you can position them on the screen. So the next group of the application framework that we'll talk about is the hardware services. So these aren't maybe critical to running your application, but these give you access to all of the low-level functionality on the device. And you'll see these more and more in the SDK as we release new versions. They're typically accessed through a local manager object, so that you don't need to worry about all of the complexities of binder and inter-process communication. And so you'll typically call the context object, get service, and give it an ID, in this case the location manager service. And so here we have the telephony service, the location service, Bluetooth service, Wi-Fi service, giving you services that allow you to scan for different Wi-Fi access points, or connect, or manage different authentications and things like that. The USB service allows you to talk to different USB devices connected to your device. The sensor service that allows you to access a compass on the device. If any of you saw the Street View demo that we did at Google I/O in San Francisco, shows how you can control Street View using the accelerometer and the compass and the device. And so these are really powerful services that give your applications low-level access to the hardware device. There's a lot more information on the application framework at code.google.com. We have, I think, a lot of really good examples and documentation in the SDK, so I encourage you to check it out if you haven't already. Okay, now the last piece, which, as Dan said, we're all really excited about, are the applications. And we're not going to talk about these a lot today, but these are, the apps that either we'll provide with the platform or you'll provide as part of, third-party apps that developers all over the world will create. And this is really why we're creating Android. We want to, foster a really rich application developer environment. Okay, let's see, how am I doing on time? That's pretty good. Android physiology. So we've talked about the different components in the platform, right? Now we'll talk about how these work together. So the first thing we'll do is go through how the system works at startup. This is kind of from, powering on the device, how all of this builds up into, whoa, I'm not clicking this and it's moving. There we go. Okay, so like on any Unix or right? I'm not sure why this keeps changing. Like on any Linux or Unix-based system, it all starts with init. So the Linux kernel, when the bootloader is finished loading the Linux kernel, it will kick off the init process, which is really the process that will control the startup of all other processes on the device. Okay, so the init process, the first thing it does is it's going to start up a set of Linux daemons. And these are low-level processes that are going to be running after startup and will control communication with some low-level hardware. And so we have our USB daemon here, and this will sit underneath the USB service and control all communication back and forth over sockets to the USB device. The Android debug bridge daemon. And if any of you have used the SDK today, you should know what ADB is. This is our protocol which runs over USB for talking with the device and being able to use a shell on the device or push applications or debug applications on the device. We have the debugger daemon that allows you to get debug information from applications. And the radio interface layer daemon. So this is a process that's always running down in the native layer and will manage all communication with the baseband or the radio. So init starts up all of these daemons, and then it starts up one very interesting process here, the Zygo process. And I think Dan will get into this in a bit more detail, but it's basically a nascent, pre-initialized Dalvik virtual machine. So it starts up and it listens on a socket for requests to create new virtual machine instances. It loads all of the core libraries and things like that in so that it's ready to go in its form. And it uses copy on write, meaning when it creates and forks a new instance, it doesn't copy everything right then. It will only copy when it needs to, when those data structures have changed. And so this keeps it very efficient. Okay, so then init, after starting up the daemons and starting up the Zygo, init will initialize the runtime process. And the first thing that does is it initializes the service manager. And this is going to be, think of it like DNS, or domain name service, for Binder. So this is going to be the object that really acts as a context manager so that all other processes can register with that if they want to be exposed through binder. So earlier when we grabbed the location manager from the context object, that's an example of asking the context, all right, I need a service and this is the name of it. And that's what the service manager really is here. So after starting up the service manager, the runtime says, all right, I'm ready to register services, so let's start this up. And it sends a request over to Zygote asking it to start the system service. So Zygote forks, like we were saying, and creates a new Dalvik VM instance, and it starts the system server process. The system service process, or server process, is going to start Surface Flinger and Audio Flinger, as well as some other native servers that are essential to controlling, the display and audio on the device. And in order for these to be used by other processes, they need to register with the Service Manager. So right after they start up, they register with Service Manager and say, and let Service Manager know that they're available for binder IPC calls. After starting up Surface Flinger and Audio Flinger, the system server will go and start up all of those core platform services and hardware services that we talked about earlier. And so it starts up the content manager, the window manager, telephony service, the activity manager, all of the core services that really provide the framework, the application framework for you to use as applications. And in the same way, all of these need to register with the service manager, and they register with a thin Java wrapper, really, to the service manager, because these are all Java services, not native. They register with the service manager to, again, say that they're available for IPC or for inter-process communication requests. So at this point, the entire Android runtime and platform is really all set up and is ready. And we have, at this point, different processes running. We have the init process that's still running, the daemons that handle USB connections and the radio connections and things like that, the runtime process, Zygote, which will stick around, and we'll see how that's important, and then the system server process, which has all of the core system services and the important native servers here. And at this point, the activity manager will make a request to Zygote and say, all right, kick off a new, I need the main application to be run. And so the application that subscribes to the main intent or the home intent is the home application here. And that will start up a new process, again, forking Zygote into a new Dalvik VM instance and load in this new process. And again, the important thing to remember here is that libc is actually running, or is actually loaded into each process here. And so it's very important that that is very lightweight and fast, because it's going to be used in all processes. And again, as you can see, the Dalvik VM is also going to be running in every other process that requires a virtual machine to run the Android code. So at this point, again, at any time when, say, the user clicks the contacts application, that's going to load a new process with a new version of, or a new instance of libc, a new Dalvik VM running in that separate process. Okay, so we've talked about the different components in the platform. We've seen how they kind of build up at runtime. And now we'll take a quick walk through how these applications communicate down to the lower levels of Android. Well, there are three main flavors of Android layer cake. The first is really an application which talks to a runtime service, or those Java services running in the Dalvik virtual machine, which talks down to the native libraries. And so we have applications which typically will call over binder IPC to another process, a runtime service, which will then make JNI, or Java Native Interface calls down through the virtual machine to a native service binding, which will load a hardware abstraction library, and that will call down to the Linux kernel, or a kernel driver, I should say. And so a great example of this is our location manager service, where an application would call, as we saw earlier, contacts get system service location manager. That would provide a handle to the location manager service, which, if it's using a GPS chip on the device, would use the GPS location provider. And that has both a Java piece to it and a native component. So that will make a JNI call down to the native version of the GPS location provider, which will load the libGPS for that specific chip. And so different GPS chips may have different implementations of libGPS here, and those will talk down to the kernel driver. So the next version is an app talking to a runtime service, which may talk to, again, one of those native services or native servers to a library. So you have the same basic flow at the top, but at this point, you're going to call over binder again to this native service. And that will load the hardware abstraction library and talk to the kernel. And a great example of this is the media framework. So when you call the media player to say play an MP3 file, that's going to call down to the media player's native component, which will call down into the media framework to decode the MP3 and things like that. But an MP3 is really only useful if you can play the audio out to the audio device. And so it's going to send a binder IPC request to play the audio out through Audio Flinger. And Audio Flinger will load libaudio, which will then play the audio out to the kernel driver. And the important thing to note here is, again, remember I was saying that there's different audio implementations in Linux, right? So people could do things with ALSA, the Advanced Linux Sound Architecture, or they could do it with, a proprietary audio driver that's maybe provided by the chipset manufacturer. And the rest of Android doesn't change, just that HAL library that plugs in. Okay, and so the last flavor that we'll go over of Android layer cake here is an app talking to a runtime service and then down to one of those native daemons. So the daemons are typically used when you have communication that you don't need to pass heavy objects or buffers around. If you need those, you would usually use binder to pass those objects around. But if you're just communicating maybe over sockets and just putting, maybe ASCII text over sockets, then you can just use a simple native daemon. And so in this case, the application is going to talk to the runtime service again, talk through JNI to the native service binding, and this time maybe just over a socket to a native daemon, which will load the HAL library and down. And a great example of this is the telephony manager. So we have the telephony manager service, which actually talks over sockets, maybe just passing the Haze AT commands over those sockets to the RIL daemon. And the RIL daemon is going to load whatever library is specific for that radio, maybe it's a Qualcomm chip or a Marvell chip, and talk down to the kernel driver or out to the baseband chip. So that's it. Those are the three main flavors of how really applications will talk all the way down to the Linux kernel. As an application developer, the great thing is you don't really need to worry about that. But it's good to know when we do open source the entire platform, you'll be able to go and look at the insides and really see how this all ties together. And so we've covered, again, the Linux kernel, the libraries, the Android runtime, application framework, and all the applications on top. We've talked about how those start up at runtime and build up the entire platform and how they talk back down through. And I'm missing a graphic, apparently. We'll move on to any questions and answers that you have. So I think there's some mics around, maybe not. Sure. Oh, we do have mics, great.
Thank you. I have three little questions. First is about the telephony function. So if a phone should work such as GSM, protocol stack, or WCDMA, product stack shows that Android has platform on some hardware. So Android has passed the SunGPP test specification of the telephony function. So this is the first question.
I'm not familiar with the Sun tests for telephony. I don't believe we're going through those, but we are going through the industry standard tests for telephony. So there's things like GCF in the States, and I'm not sure what the applicable standards are out here, or standardized testing. But we are submitting the platform on reference hardware to go through all of these different standardized tests.
So I think it has a long way to go. So the second question is about the SIM card. The Android has support the smart card. So you know that telecommunication operators like the smart card. So has the Android support smart card or SDK?
We will support SIM Toolkit.
Yes.
SDK on the platform. I'm not sure to what extent we'll support smart card on top of SDK.
Okay. The third question
question
is about the Java virtual machine. The Dalvik convert the Java bytecode to the DEX bytecode, but also use the Java technology. Should the Android pay the license fee to the Sun microsystem?
So it's a good question. But remember that Dalvik doesn't actually convert those. So class files and jar files are converted at build time. So in the SDK, we run those through a tool that converts them to Dalvik bytecode. Okay, and so Dalvik is actually not a Java virtual machine. It's a different virtual machine that uses different bytecode format. And Dan will get into the details of that. But so it's actually not executing Java bytecode.
So
applications are written using the Java programming language, but they don't run in a JVM environment.
So Android should need to pay any license fee to the Sun microsystem.
I can't. I'm not a lawyer, so I don't know the details there. The technical details are our bytecode is not running in a Java virtual machine.
Okay, thank you.
Yep.
I have two questions.
Yeah.
And one, you say Andorra is Java programmers may be familiar with Andorra. So does Google provide any manual for Java programmers help them to program in Andorra?
Yeah, so we have a lot of documentation online as part of the SDK that gives you, we have sample applications in code that we've submitted. And we'll be, as part of a lot of these developer conferences, we'll be making the presentations available online and more sample code and more code labs that show you best practices for developing Android applications. But there's a lot of documentation online for how to write applications for Android.
So that will take a long time for a Java programmer to program?
Oh, no. I think, did Jason not go through example with his laptop? So you can build applications in a matter of minutes and have them deployed on the emulator and running. It really, if you're a Java developer and you're familiar with the J2SE environment, you'll be able to get started with Android very quickly.
And the other
part of your question. Actually, right now we have another. We are in a different conference room hosting a code lab for Android. Where our engineer will show you how to build a simple application in minutes.
And the second question is, you just say an application to request a system service, so she passed the request for the service. And I have saw your picture says, and there is a system service manager. So every system service may address themselves in this system service manager. So my question is, does the application to post his request to the system manager or just post his request to the system service?
Right. So applications will use a context object. And so each activity actually inherits from application context, I believe, or context. And so they will use that to get a handle to the service. And so your requests will actually go directly to the service running in that separate process, but in order to get a handle to that service, you need to go to the service manager to get that.
Thank you.
Or behind the scenes, it goes to the service manager. You just request from the context object. We have microphones elsewhere. Sure. Yep.
Thanks for the speech. I have two questions. First is, I have not seen some Android support some handwriting devices or touch screen devices or multi-touch screen devices. So, will these devices be supported in Android?
So multi-touch is, I don't believe it's supported in the platform now, but there's nothing really core to the platform that would prevent it. So, I think for right now, Android doesn't support multi-touch, but it may in future.
Oh, okay. The second is, you have shown us the sophisticated structure of Android. And is there any benchmark result to show us the performance, overall performance, and battery duration? Thanks.
For actual performance and benchmarks, I think Dan will go over some of those with respect to Dalvik and the space savings that we've made. In terms of battery life and things like that, we don't have benchmarks that we've published yet. But we will make those available as actual hardware starts to get out into the markets with Android running on it.
Okay, thank you.
Yep. Anyone else? Yep.
My question is, what do you think is the biggest advantage for the Android to develop a mobile game?
For a mobile game?
Yeah.
That's a good question. I think there's a couple really big advantages. I think, the rich graphics library that we provide with OpenGLES, the unique services that we provide, like the location manager and some of all those other services that give you access to different things on the device and allow you to do mobile mashups. So we have, as part of the Android Developer Challenge, we had a lot of people that were building applications that would use the map view or the web view and things like that. So I think really it's the application framework in general that gives it a big advantage. It's very easy to develop things there. So I think those are the big advantages.
I have a question about the VM actually. So I have a confusion here. So could you go back to the slides show the layer interaction things?
Yeah.
Okay. So we have a VM here, right? So all the Java code is supposed to run on VM, but you have JNI here. So is that the same layer? Or?
Yeah, that's a good question. So I don't have the VM actually called out here. But all the code in blue up there is running within the VM. And those JNI hooks actually go through the VM out to native code.
Okay.
So yeah, it was a bit easier to draw it this way, I guess.
Okay. So it's pretty much the same as is that JNI interface the same as the standard Java JNI interface, or you have your own?
Yes, it's the same. Well, yeah. So yeah, it's the same.
Okay.
Thank you. We have seen that Android is a relatively complicated system, and as I see yesterday, that Steve Jobs declares that for mobile system, maybe one active process is enough, which will save the energy and the CPU time. How do you think about it?
Well, that's a good question. I think that's one of the major things that distinguishes our architecture from others. If you think about, maybe you have a service running in the background that you want to notify you if some of your friends are nearby. Maybe this is a social networking app. Well, if only one process can be running at the same time, then maybe if I'm playing an MP3, I can't have this other service notify me that a friend is nearby. Or that's a simplified example, but I think there's a great case for having multiple processes running at the same time and multiple services running in the background as you're doing something else. The main thing that it's important for the platform to take care of is how are the system resources managed. You don't want the user to worry about having to shut down different applications or services to conserve battery power or CPU power. And so that's one thing that Android handles for you. When we don't go through it in these talks today, but there's actually Androidology talks online that you can look up on YouTube that will explain how Android handles cases where the system resources like memory may be running low and you have an application running in the background. And Android can actually save the state of that application, remove it from memory, so it's no longer using the CPU, no longer using memory resources, and then restore it if the user goes back to them. And so what this allows us to do is really create a seamless navigation experience on the device where you can do mobile mashups. So think about it like navigating through a web browser, where you can go from one web page to the next, and then back. And you don't need to worry about the state or closing down old web pages before you open up new ones, right? Those are always there for you, and that's what we're really enabling on Android. All right, I guess one more question, I think. Sure.
Okay, thank you. I have one question. As you mentioned just now, the location service is one service supported by Android. I have a question. Is the GPS location the only one supported by the location service, or you will tend to other systems such as GLONASS or other technical methods?
Yeah, so that's a good question. We, the location service does not rely on GPS being on the device today. And so Google actually has a location service. If any of you are familiar with Google Maps for mobile, where we call it My Location, and that's actually uses cell tower locations to figure out approximately where the user is. And so we have that technology built into the location service on the platform. So even if the device doesn't have GPS or some other physical hardware location device, we can still grab an approximate location for the user.
Thank you.
Okay.
好，我们感谢这个 Patrick 给我们一个非常精彩的这个讲座，我们用掌声欢迎 Patrick。